Hi, I'm Mary. Welcome to my channel. In this video, we're going to be going over some concepts about functions and graphs of functions. What we're going to be working on is we're going to look at rational functions, whether or not they exist, and just go over this idea of range and domain and increasing, decreasing, and constant intervals for the function. So if you want to work along, there is a worksheet posted in the description box. Okay, so the first question presents f of x as a rational function. I say it's a rational function because it's a function. It depends on x. And it's rational. The expression is rational, which means that it looks like a fraction with a numerator and denominator that are polynomials. So the question asks, find f of 3 if it exists. So kind of tucked into that question is, does f of 3 exist? You have to see this question and untuck it. This one will come up. This is an important question. So does f of 3 exist? Is the same as f of 3 exists when the denominator does not equal 0. Okay, so this is the same as, is the denominator not 0? Is the denominator not 0 at the question, at the x in the of interest, right? So is the denominator not 0 at x equals 3? So let's go ahead and look at the denominator. 2x minus x cubed. And let's check at x equals 3 what it is. So it's 2 times 3 minus 3 cubed. 9 minus 27, which is not 0. Well, that's a good thing because that answers the question, does f of 3 exist? Yes, it does. And what I've done here is shown my work so you could follow my reasoning. Okay. So now that we know that f of 3 exists, let's go ahead and evaluate the function at x equals 3. Let's find f of 3. F of 3 is equal to, substituting in, 3 squared minus 5 divided by 2 times 3 minus 3 cubed to the third power. Numerator. So the fraction bar works like a parentheses. So we're going to do numerator and denominator. And just follow along, check our work. So I get 4 over minus 21, and this is written. We'll take the negative sign. The negative sign can come. This is positive over negative, so the fraction itself is negative 4 over 21. Okay, that's how you do number 1. All right, we're going to move on to number 2. Number 2 says, find f(2) if it exists. And again, it is a rational function. Okay. So we're going to, the first question is sort of tucked in. Does f of 2 exist? That's the first question. So let's go ahead and answer that by saying, restating it to, is denominator not 0 at x equals 2. Okay, so let's look at the denominator. Okay. Calculated at x equals 2, we get 2 times 2 minus 2 squared, 4 minus 4. Wow, that does equal 0. So here is an example of a situation where the function doesn't exist at the given value of x. So does f of 2 exist? No. And again, below here is how I tried to show my work so you would understand. All right, I'm going to go over to look at to share my screen and look at the worksheet for a moment. Okay, so this is this is the linked worksheet. So I did the first 2. Go ahead, you can work on the next 2 if you like. And I want to just take a moment and go over this idea of domain of a function. So we had earlier talked about the domain of a function, but we had only used it in the context of like a small set of elements that the function was acting on. But now I want to just go into the more general. Most of the time we'll be working with axes, the Cartesian XY axis. And so I'm kind of thinking about it, just restating it in terms of that. So the domain of a function is the set of all possible values of the independent variable, often, but not always, denoted x for the function. So f of x, then x, okay? And then the range of the function is the set of all possible values of the dependent variable y. All those values that it can be taken on, that makes up the domain, that makes up the range. So if we look at every x in the domain and we see what kind of y's come out, the set of those y's is the range. Okay, so I have a couple of problems here. I'm going to just do them with you. Okay, so we're going to look at the graph on the left and determine the domain and the range. And we're asked to express the intervals in 2 different notations, the interval notation and the set builder notation. So we'll do that. We'll get a little practice with using the 2 sets of notations. So the domain is the set of all of the x values, all possible x values that the function takes on. And in this case, it looks as if the function is taking on all real numbers. So we'll go ahead and express that. Minus infinity, soft bracket minus infinity to infinity. And in set builder notation, it's curly brackets, it's all x such that, and I'll go ahead and borrow my symbol here, minus infinity is less than x is less than plus infinity. And then we close the curly bracket just to be really accurate here. This should be a lowercase x. It should be the same symbol as I'm using here in the inequality sign. Okay, so that's the domain, how we express all real numbers in those 2 sets of notation. Okay, so the range are the y values that get taken on as we consider all possible x values. And so in this case, we see that the function takes on values 4 and all values between 4 and 7, and it takes on 7. So let's go ahead and right? So I'm going to use the square bracket here for the interval notation because the 4 is actually taken on. It's not just approached, but the function actually takes it on, and also goes to 7 and another square bracket. So that's the interval notation. And then in set builder notation, we're going to look at all x such that x vertical bar, and it's 4. And since we're working with that square bracket, we use the less than or equal to sign. If it was a soft bracket, it would just be a less than sign because it indicates that 4 is included with the equal sign. Okay, so in set builder notation. Okay, so you guys can do that one if you want on your own. And then we're going to come down here and look at intervals where the function increases, decreases, or is constant. All right, so let's look at this graph on the left. And we're asked to find intervals where it's increasing, decreasing, and constant. So let's just go ahead and look. So in this guy here, and this first long flat extension, that's constant, and then that goes to -2. So that's an interval of constant. Let's go ahead, I'll go ahead and write that here. It's an interval of where the function is constant. So we're going to go from -infinity and then all the way up to -2. And doesn't matter. I'm going to include the -2 because at 2, it looks like at -2, it looks like the value the function is taken on is still this 4. It's constant up to that point. Okay, intervals of increasing. So we increase from -2 to -1. Going from left to right, and I'm going to put each interval in whatever category it belongs to. And then we see here when x is -1 that it begins to decrease, and it decreases until x equals 2. I am looking for the x values. It's interesting what the y values are, right? But over here, I'm supposed to put intervals of x values. And so from x equals -2 to x equals +2. No, excuse me, from x equals -1 to x equals +2, I am decreasing. Okay, and from here, this point, I'm at x equals 2. The function begins to increase and it continues to increase. So let's go ahead and put that also as an interval of increasing over here from 2 to infinity. Okay, so we kind of got all of our intervals laid out. And I left a couple for you guys to do on your own there for a moment. Okay, so scrolling down to number 7, we're asked to consider the graphs and find the relative maximum and minimum if they exist. So we're looking for relative max, relative min. And we come on over here, we notice this cubic equation. And here it comes up. This is a relative maximum because in the interval around that value, all the other values of the function are less than it is at here. It's not that there's never another point on the function that is greater than it, but it's relative in its interval, immediate interval. F of 0 is a maximum in that interval. So the relative maximum, there's 1 at x equals 0. And when recording a relative maximum, we want to give the ordered pair. Okay, so it's actually not the x, but the x and the y. Okay, and so in this case, we're saying when x equals 0, the function is 1. And we could check that in here if there's a question, but I chose unquestionable points. Okay, so 0, 1 is a relative maximum because the interval around 0, 1 is the highest value of the function. And we see here another relative extreme point. And let's okay, and we see that when x equals 2, y is equal to minus 3. Okay. So when x equals 2, y is equal to minus 3 is the relative minimum. Okay, and we have one for you guys to do on your own. Okay, I wanted to, oh, actually, I'll do this piece and then you guys have another set below it. Okay, so here's another function. And on this function, I'm looking for, it looks like only one relative extremum. In this case, this point right here, this is a quadratic, x squared minus 4x plus 1. And we see right over here, there is a relative minimum. It occurs when x equals 2, y equals minus 3. So let's go ahead and pop that in there. When x equals 2, y is minus 3. And I look for a relative maximum, but none exists because in this function, as x moves to goes towards plus infinity, we see the behavior extending up to infinity. And the same for as we move x towards minus infinity, it's also going up. So there are no more relative points. So put that in there. Okay. And a couple for you guys to do. And that's it for this video. In the next video, we're going to move forward to the piecewise function, its definition, and how to graph it, how to evaluate it, and how to graph it. So I'll see you there.